Good morning, everyone. Welcome to the 2024 Virginia Water Well Association Virtual Education. This is course two in our track this summer. And we have this morning David Bumbleow with Franklin Electric. He'll be presenting the course topic of pump basics and advanced stray voltage. David has presented for us multiple times and has a great value to the association. So we appreciate your time this morning. And a little background on David. He is a senior field service engineer with Franklin Electric, a global leader in the manufacturing of submersible motors, pumps, and controls for the water and fueling industries. He has over 28 years experience in the water well industry. His primary responsibility is to offer technical support and training for professional water well contractors. He currently covers a four-state region, which includes North and South Carolina, Virginia, and Tennessee. He graduated with a Bachelor of Science in Business Management from Indiana Wesleyan University and has an Associate in Applied Sciences degree in Industrial Technology from Ivy Tech State College. He's a licensed journeyman electrician and certified HVAC installer. He currently resides in Tennessee. Thank you, David.
Thank you, Christina. Welcome, everyone. And as she had mentioned, this is a two-part series. The first part is going to be basic centrifugal pumps. I'm going to walk through the design and operation of a pump. We're going to do a sizing exercise. And at anytime during this presentation, if you have any questions, please don't hesitate to ask. I've done a few of these before in the past. They are a little different than actual live presenting. And the fact that I can't see you all. So I'm not sure if I'm being boring or not, but I'll try to keep it interesting. So as we go on, I do have a pointer that I will point out some of the different aspects and designs of the pump. I will also try to, do my due diligence to highlight exactly what we're talking about during this presentation. But in our industry, for the most part, a centrifugal pump is the number one choice of pumping water and or fuel. There are many other uses for centrifugal pumps, but in our arena, that's what you're going to see the most of. And the term centrifugal actually comes through centrifugal force, as you see here. Through a centrifugal force, we're going to take that water molecule and move it to a point of discharge where it can be used and or transferred. So in our arena, it makes up about 85% of the pumps worldwide. And as we go through this, that's going to be my main concentration is that centrifugal pump. Now, in most cases, that submersible pump and or above ground pump is usually powered with an electrical motor. There are many other ways of being able to drive that pump. You have a PTO shaft that you can attach to a pump. Farmers do it all the time. They'll use their tractor to drive that. There's belt and pulley. There's a number of ways, but in our arena, we're using an electrical motor. So there opens up Pandora's box there for other things that has to accompany this. You know, what kind of supply do we have? What voltage levels do we have? And then distances make up a big part of this. Unfortunately, we're not going to get into that part. That's probably another hour or two. So we're just going to concentrate right today on, what is a submersible pump, what drives it, and then kind of lead off from there with, like I said, a sizing exercise. So in most part, I throw this centrifugal pump up here. It's an above ground. One of the issues that come to my attention quite often is a new product being installed, and they hook it up. They start to use the system, and they notice it leaks between the pump and the motor. Well, that is due to this mechanical seal right in this general area right here. Two things that you've got to be cautious of when dealing with a pump. The first is every pump that is out there unless it's a submersible, of course. You have to prime it. You have to add water to it. These seals are compressed seals, and if they are ran for any moment of time, they could get damaged due to friction. So you've got to be very careful there. The other thing that you got to be careful of is dropping it. And I know sometimes that's out of our, out of our, ability to control, especially when it's getting shipped from point A to point B. So if something like this should occur, that's typically what's going on. One of the two things has happened. It's either gotten dropped or bumped, and or it's been run dry at some point. So I know there's been some cases where installing contractors would bench test it, so to speak, just to make sure everything is working correctly before they take it to the job site. So just remember that every pump has to be primed before running it. Otherwise, you can damage those seals. So the two main working parts of a pump are the impeller and what is referred to as the volute, or in most cases called the bowl. The impeller is the moving portion. It's what's connected directly to the shaft of the motor. So in our case, the electric motor is going to spin that impeller. Now, it is directional. It does need to be spent in the right direction to make sure that the flow of water is correct. We're able to build pressure and move that volume of water. So when we're looking at this basically the pump itself, as the impeller is spinning, we refer to that as velocity energy. So in the eye of the impeller, which is an essential portion here, a water molecule will be basically grabbed by the impeller through natural gravitational force. When it is in the impeller or the eye of the impeller, as it is spinning, it will eventually make its way out to the outside edge. So we're in allowing that velocity energy to give us the pressure energy to be able to move that volume of water plus build pressure in that system. So as you notice that the curvatures of these, basically they're referred to as vanes. If you think about it, there are some pumps out there that the vanes come straight out. Well, if you look at the surface area of that as it comes straight out, it is a lot smaller. And for us to make the pump as efficient as possible, we want to hold on to that water molecule as long as we can. We're trying to make sure that that velocity energy is impacting that water molecule as much as possible. So to be able to hold on to that water molecule longer, what we do is we put a little bit of a curvature to that vane so we can hold on to it a little longer. And in most cases, these type of pumps are not very efficient. As a manufacturer, we try our due diligence to improve the performance, keep from recirculating. And what recirculation means is as that water molecule is removed and it starts flowing out of the volute, sometimes it will try to recirculate back through this section right here to get back to the eye of the impeller. And so therefore tolerances have been tightened up on that, along with some sealing methods to ensure that doesn't happen. Well, in the early days, that was acceptable, just due to, we knew what we had. The efficiencies on this particular pump are lower, but due to Department of Energy requirements, especially with pump manufacturers and or motor manufacturers, that bar has been raised. So we as a manufacturer, and along with others that are out there, have to improve their pump efficiencies. Well, in the early days, where that wasn't as strict, there was a little bit of recirculation there, which was okay. The tolerances wasn't as tight. So therefore, if we were to pick up any particulates, like a little bit of sand or debris while pumping, it was usually easy enough to be passed through and pushed on out the end of the pump. Today's pumps are a little less forgiving. If you get too much sand and or particulates in the water that you're trying to move, what can happen with today's pumps? They could cause them to misbehave. It could cause wear, and it can cause loading issues, mechanical drag, and things like that. So you've got to be very careful there with today's pumps. You want to make sure the screens are in place. If you're dealing with an above ground type piece of equipment, you want to make sure you've got your screens and protection in place there for those particular pumps. So as we move on, as we are talking about the impellers, there are a whole lot of different designs out there. The three basic types that we see are the radial style, which you can see up here at the very top. They are the most common in our industry, followed by the actual, which is basically a prop. We call it a propeller, which you'll see mostly in the marina section, like on boats and so on and so forth. There are mixed flow designs, which you'll see in some of the larger pumps, such as turbines and a lot of the bigger volume type pumps, especially if we're trying to increase flow. Those are the best designed for that application. And it does, the efficiencies do move up quite a bit with those mixed flows. Now, given that, when you're talking about radial pumps, there are different designs inside that arena. We've got semi-open. Okay, you see a lot of these particular types used on like fan or moving of air. If you were to look at an above ground motor, you can see this type where it's designed to move air and to push it across the motor to keep it cool. We also have this type in a pump, which, in most cases you're not going to see unless you tear it apart. We do have some enclosed, which are a little larger design. They are designed to handle solids. It's referred to as a non-clog. Most of the time you'll see those in the wastewater or some kind of gray water application where it's moving larger, I should say, debris or particulates. And you can imagine, without us going into more detail. And then you have another style. It's basically enclosed. You'll see a lot of these. We refer to this particular style as a pancake style. It's the most economical, the most common that you'll see in our industry. And, given its durability, easy manufacturing, that's why it's the most popular in our industry. And it has some other benefits to it. As we go on, I'll explain those. But inside that, basically a submersible pump, you'll have that impeller that is basically a diffuser surrounding it. That's can be also referred to as the volute or the bowl. And what happens as this impeller is spinning and it moves that water molecule, the diffuser actually guides it to the next stage. Okay. And in most cases, you're going to see a multi-stage pump. Okay. So when we put multiple stages together, ultimately what we're trying to achieve is we're trying to build up pressure. These are typically going to be set in a deeper application. We're having to lift that water to the surface, which may be some distance down in the well. And then plus, we've got to be able to build up pressure for the application that it's involved in. So now that we're on the subject of pressure, there's two ways of measuring pressure. We can do it either, in pounds per square inch, or we can do it in feet of head, which both are crucial for our calculations and or sizing and determining what the system is doing. PSI, typically measured with a pressure gauge. And honestly, it's more just to see what the system is doing and how it's operating. We can also convert that to feet of head, and I'll show you that conversion here in just a second. But feet of head is basically the equivalent to that. And when we're looking at feet of head, we're basically looking at the elevational changes from where the water is in the well to where its point of discharge is going to be. pumping levels included in that, along with any kind of friction losses. And we'll cover all those as we go through the next few slides. The two calculations that you will need to memorize and or write down and use. One of them I use most often. I hardly ever use the top one, which is the equivalent to 1 foot of water column, right? So it takes in consideration just what that 1 foot is going to exert in pounds per square inch at its base. And in this particular exercise, it's 1 foot of water column will basically equal 0.433 psi at its base. Okay, so it doesn't matter if you're measuring, if you're looking at an ocean or you're looking at a swimming pool or you're looking at a, glass of water. At its base, it is what we're actually measuring, and it's pounds per square inch, psi. Now, the conversion that I use the most is 2.31, and I'll show you in a couple exercises here in the next slide. But as we look at this, basically 2.31 feet of water, if we were to measure at its base, we would see that it equals 1 psi. And that's the most common conversion that I use the most of, as we'll see in this exercise. So if I was to take 200 feet ahead, basically multiply that by 0.433, I'm going to come up with about 87 psi. So that's one way of using the 0.433. The one that I use the most are basically the two bottom calculations here. So if I've got 50 psi on my gauge, that's equivalent to about 115 feet ahead. Now, granted, these are all rounded up. If you use your calculator, you're going to see there's basically a decimal in there. So we usually round up to the nearest, the next digit up. So 50 times 2.31, okay, is really equivalent to 114 point something. Sorry, I'm not got a calculator in front of me, but equivalent to 115 if we round it up. If we were to take 46 feet ahead, it's equivalent to basically 20 psi. And with a calculator, you're just taking 46 divided by the 2.31, and I can assure you that's like 19.9. So we round that up to 20. So there's how you're going to convert back and forth, and that'll become more obvious when we get down to sizing a pump. We typically will lead off with feet ahead. So we're lifting that water molecule from a distance in the well up to the surface, and then from the surface, maybe elevational change plus or minus. Plus, we have to satisfy usually some kind of pressure device that's telling the system when to turn on and turn off. So that's where we're going to convert that PSI. Okay, so as we go through here, I'll have another exercise. We'll go over that, converts that, and keeps it all in one form or the other. So as we look at sizing a pump, there are basically two things that we need, especially when it comes to sizing a submersible. Oftentimes what happens here is that we try to, as the well is drilled, they don't want to the installer or the driller does not want to over pump, but that's not the correct way of sizing a system. The proper way is to size it for the application, okay, not what the well produces. There's other things that we can do if the well is not a good producing well, and I'll cover those in just a second. So the two things that we need is basically the gallons per minute for the application. A few questions will need to be asked, and in some cases, there are things that are out of the installing contractor's hands. I think it's vital that as an installing contractor that you have a good relationship with the actual building contractor. And when he subcontracts out, the plumbing inside the home, I think we need to educate on the size of the pipe, because a lot of times we run into friction issues. We're doing everything we can on the well side, but what often happens is when we get to the application, the size of the pipe has been reduced and or there's a lot of restrictions. We ended up totaling up friction loss pretty high in that application. And therefore, if we've got an application where, say, a bathroom is at the end of the hall, clear down at the other end of the house, opposite of where the water comes in at, it may not flow the water properly, and or multiple items inside that bathroom may not be able to be used at the same time without seeing a pressure drop. And that is due to the size of the pipe, the restrictions, things like that. So it's in everyone's best interest to make sure they have a good relationship with the contractor or the building contractor. Now, granted, if some of those, if that cannot be addressed, then sometimes we may have to crank that pressure up just to offset for friction losses. But in this particular exercise, we're going to need what the application needs, and then how much pressure it's going to need, or need to satisfy the switch and or the application itself. There are two means of figuring up your gallons per minute. I prefer the fixture count method. There's also referred to as the peak demand method. Once we have the gallons per minute, we're going to move on to, TDH, total dynamic head, which includes three factors. The first one is, what kind of delivery pressure do we need for the application? What are the elevational changes? Where is that water being brought from, and where is it going to be delivered to? And then we're getting it there through a piece of pipe in most cases. So we have to figure out friction loss, which includes many different factors. Friction loss could come in the form of basically T's, 90s, the size of the pipe, and we'll go over some of that here in the next few slides. But we have to take that in consideration. That can add up to basically increasing the horsepower to overcome that friction loss. And I'll show you some tricks of the trade here to combat against that, and things that you may or may not have thought about in the past when it comes to that friction loss. But as we go on, for many, many years, I had this particular slide up, and I would talk about it, counting up what fixtures in the home or application uses water. And the way this works is you assign 1 gallon per minute to each thing that uses water. And so as I went through this presentation, I noticed I overlooked something. And I did pencil it in, as you can see there. I forgot about adding the refrigerator. So even though it's got an ice maker and a water dispenser, and it uses very little water, the bottom line is it still uses water. So you still have to count that as an item that uses water. So as we go through the home, let's say in this example, we have 2 full baths. The way it's been explained to me is usually you have 3 fixtures in a full bath. You usually have your toilet, you have your sink, and you have typically a shower or a bathtub. Now the shower and bathtub, because you're not typically running those both at the same time, it's one or the other, that just counts as one. So if we've got 2 full baths, we basically got 6 fixtures. A half bath usually consists of a commode and a sink. So there's 2 fixtures. You go to the kitchen, you have a kitchen sink, you have an ice maker. Oh, I guess I did put that in there. There you go, ice maker and refrigerator. So we can scratch one of those off. But nevertheless, dishwasher, wet bar. As you can see, we've got a wet bar here. And what you don't see is out of the picture, there's a sink over on the other corner. And then outside, we have 2 outside taps. So as we add these up, we come up with 15 gallons per minute. Okay. Now the question comes up, well, my well's only a 5 gallon per minute recovery. Well, okay, so we'll take that in consideration when we're sizing the tanks, and or if we deem necessary, we may have to put in a storage tank and boost it from there. But we never want to short the house. Okay, so if I put a 5 or even a 7 gallon per minute pump in this system or in this application, I'm going to run into all kinds of issues and problems. So I try to stay away from that. When you ask me to size a system, this is how I'm going to do it, and it pays off in the long run. And again, like I said, I'm either going to oversize my tanks, or I'm going to add a secondary storage tank and then a secondary pump to provide pressure to the house. But I'm never going to short the home from this calculation. Now, the peak demand method is a little different way of looking at sizing a system. The way it works is you take up and you look at what appliances in there could be running at the same time, and then you're going to multiply it by 3. So as we look in this example, and again, this is a guess. I don't like doing this because it opens up too many what ifs. Like a shower, we could take in consideration both showers are going. There's a dishwasher and maybe, something in the sink and or some kind of use there in the half bath. And then, coincidentally, maybe the sprinkler system kicked on. But you got to be careful there because the sprinkler system can pretty much use up that 15 gallon per minute by itself. So you've got to be careful there. And then in today's, homes, we have to worry about full body showers. So if we've got a shower in there that is unconventional, meaning that it's got multiple heads inside the shower and uses quite a bit more volume than just a normal shower, you may get into trouble here because I've seen in some cases, the shower feature is using 10 to 15 or even more than that just for it to function correctly. So we've got to be careful there. And those are questions that we need to ask the building contractor and or see for ourselves when we're making this calculation. So as we go through, I'm just using this as a standard calculation. We're going to see that there's 5 items in there. We're going to multiply by 3, and there's where our 15 gallons per minute comes from. So if we were to take a look at a pump curve, and of course, as we're looking at this pump curve, you'll notice this is a 5 gallon per minute pump curve. And as you can see, we're not going to get to 15 gallons per minute off of this. We're only going to achieve 5. So if we do have a shower going, a dishwasher, maybe something else in the kitchen, you're going to grossly overshoot that 5 gallon per minute performance. So the whole purpose of this curve is to kind of give you an idea, what are we looking at here? I prefer the curves here. They give me a better idea of what's going on. Most manufacturers will tell you exactly where that pump range is able to operate in. So a 5 gallon per minute pump, it shows here that it will successfully go down as far as 1 gallon per minute and as high as about 7.5 gallons per minute on this particular design. Where we want as a manufacturer, because of efficiency requirements, we want you to stay somewhere in this grayed out area where it's called the best efficiency range. That's where I want to perform. I want my pump size based on this area here. Okay, so as we start adding up for our TDH, we're going to look at delivery pressure. We're going to look at evaluation or elevational changes. We're going to look at friction loss. And then once all that's added up, that basically transitions into what horsepower is it going to take to move this volume of water. And so as we go through this exercise, you're going to see that we can get in some trouble once we get past a couple points here I want to make first, and then I'm going to harp on pipe sizing, which is very crucial. And that can lead us into some issues. So first thing we want to look at is delivery pressure. Sometimes we may have it on a pressure switch. We may have some kind of sensor, such as a transducer, or some other means of monitoring what that line pressure is. Well, we have to convert that. So as you look at, say, a standard pressure switch, say we installed a 40-60 pressure switch. Well, we're looking at the bigger number. The bigger number is what shuts that system off. So our pump and motor has to be able to develop enough pressure to satisfy that switch to turn it off. Otherwise, we get a run-on situation. Okay, so we're going to take and convert that. Since most of what our calculations consist of is basically lift or total dynamic head, which we're going to convert to feet of head by doing this simple calculation. We're going to take 60 psi times 2.31, which is equivalent to 139 feet of head. Now, in my exercises, I always round that up. So I'm going to use that as 140. I don't mind to round up just a little. You don't want to overshoot too much because that drives the horsepower up. And as I go through this, you'll see why that's a bad thing. So as we start adding the calculations up, we're going to also take a look at where that water is coming from. Now, this is where it gets kind of tricky. If it is a low producing well, the water may start up here somewhat high in the well, but then drain down or pull down to what we call a pumping level. Okay, so if we only have so much water coming into the well and we're pushing out a bigger volume than what the well is producing, then we could basically draw that water level down. Now, I always put two numbers to this. I will draw basically a line, makes it look like a capital T. On one side, I will put where does my water start at, which may be a upper level. On the other side of the T, I will typically put where the pump is set because the water level is never going to draw down past the inlet of the pump. Okay, so and if it does, then you have major problems at that point. So those are the two numbers I will use, where it starts at and then where it's going to end up at. And so I'll use that calculation when I go to size my pump. Now then, once we get it to the surface, we may have to count for any elevational changes, up or down. Now, if it goes downhill, that's just a plus for us. That means the pump doesn't have to work as much because gravity is going to help us at that point. Where we run into trouble is if we have to lift it up to the application. So that we want to take that in consideration. So in this case, our pumping level, just to make the math easy, is 40 foot. Our elevational change is 70 foot, okay, from the top of the well. So we will take those I've got a little cheat sheet that I use to calculate all this up. The third function we have to look at is the friction loss. And this is where it gets a little tricky. I know oftentimes if it's a standard pump that's being installed in the well, 1-inch pipe is typically what is used. As a manufacturer, and some of my years early on was spent in an engineering lab where I tested and developed a lot of these products. The rule of thumb is whatever the pump discharge size is, that's what we're expecting you as a manufacturer to use when you're installing this. So I can assure you that most of the smaller volume moving pumps are 1 1/4 inch discharge. Comes to mind only one pump that's out there in our industry that may have a 1-inch discharge. I don't usually name drop, so for those of you that's been in the industry long enough, you probably know which one that manufacturer is. But long story short, 1.25 inches is what we're planning on you to use. That's designed around the volume that we're trying to push, and as a manufacturer, we're looking at those friction losses to keep our horsepower under control, because that opens up several other questions and or things that you may have not thought about going forward that the homeowner is going to have to address, such as utility bills. So as we look at friction loss, the size of the pipe, the material of construction, the length, that all contributes to that friction loss. Plus, on top of that, we have the fittings and check valves and other things that are in that line that will add up into friction loss that we sometimes overlook. So if we're looking at that pipe, the material of construction makes a big difference. The slicker that material is, such as some of your PVCs, they are a slicker material, so therefore you're going to flow that water a little easier. So the calculation for that is less than let's say steel pipe or galvanized pipe. It's a little rougher material, therefore friction loss goes up with those materials. So you got to be careful which ones you're choosing. But I understand, the difference between them is, the weight that it can support, the pressure that it can support. So you've got to pay particular attention to what pipe you're putting in there and the material of construction so that you don't end up damaging the pipe, getting into a situation where the product falls off the pipe because of the weight, and or sometimes a run-on situation where temperature may affect the PVCs and cause them to do like a ballooning action. That's totally different subject, and I don't have anything to show you representing that at this point in time. So just keep that in the back of your mind when you're using the PVC materials. Most of the time, there will be a chart that reflects. If you don't have these or you're unfamiliar with them, I got to be honest with you. I'm a firm Googler. If I don't understand it, I'll Google it, but don't typically take the first thing that pops up. I usually do research, and I go to multiple websites and do my own investigation. But there are charts out there that will help you. I'm on a name drop. Most of the time, I will use like the Hunter or the Hunter books, and or some of the equivalent manufacturers for irrigation. They do a pretty good job of putting these charts together, showing friction losses, velocity in the pipe, which is another thing that you got to be concerned with. We don't want to exceed the water flowing in the pipe past 5 feet per second. And so you'll see a lot of these charts, they'll reflect that volume or in measured in feet per second. You want to stay under 5, which if you get to that point, what happens is you can start, especially if it picks up particulates in the well, you can start sandblasting the material. Eventually you'll blow a hole in something. And or if it's making a 90 and or a T connection, you can get a little bit of what we call water hammer in the system. So you want to be very careful on that velocity. But as we look at this chart, it's basically sizing it in 100-foot lengths. So if we were to, put in, say, 1-inch drop pipe, and we're trying to flow 15 gallons a minute, and as you can see on this chart, we don't have a 15 gallons per minute, so it's going to be bounced between 14 and 16. But as we come across here, if we were to hang that on 1-inch pipe, you're looking at somewhere about 18 foot of head loss per 100 foot. And if we were to go up one pipe size to 1.25 inches, now that drops down to about 6.5, just under 7. So it's almost a factor of 4 just by going up one pipe size. I'm sorry, I was looking at the wrong column. But you're looking at about 4 here versus, over here at this corner at 18. So you can really dramatically cut that friction loss down. And what that's going to do is that may save us in horsepower. So as we still continue to go on looking at friction losses, we also got to take in consideration our 90s, our T's, check valves. That all adds up. And as you can see here, they add up pretty quick. So 1-inch 90 in this case is equivalent to 2.7 foot of head loss. Okay, so we want to make sure we can, take a look at that and add that in as well. This is the cheat sheet that I was referring to earlier. There are 3 sections to it. You have basically, what's above the well. You have, your friction in the well, and then you also have your system information. And so as we go through, we'll start plugging in some of those numbers. So let's just say above the well, we've installed 1-inch pipe. Okay, it's a distance of about 200 feet. We've got about 4 90s and 2 45s, no T's. We'll go back to the chart and you see what that equivalent is, and we'll add all this up. Now, as we go in the well, we've got it hanging on 1.25 inch, Schedule 80 pipe. It's roughly about 60 foot down from the surface down to the pump. And then our operating conditions. The system head information. We have the pumping water level set at 40. We got an elevational change of 70 feet. And then we've got to satisfy our 40/60 switch. So we're taking the bigger number times that 2.31, which is equivalent to 139 feet ahead. So as we add those up, we go back, we snatch those numbers that are equivalent to the 90. One thing I point out here is if you can use 245s to accomplish the same 90, you'd be at 2.6. I know you're scratching at the surface, but it's interesting in how they calculate these friction losses up. So if you think about it, it's less of a sharp bend when you're looking at a 90. So as the water's flowing up, it's basically shooting at a 90-degree shot, where on a 45, it's more of a smoother transaction, especially if you got a second one here that's still equivalent to 90. It's just not as sharp of a turn. So you're losing basically a 0.1, which not going to add up much, but a little bit here, a little bit there, that does make a difference. So as we go back and we plug those numbers in, it says those 490s are equivalent to about 11 foot of head loss. The 245s are equivalent to about 3. So we add all that up, and we're somewhere around 214 on the above well losses. Friction in the well, we're going to take a look at that as well. On this next one, we look at the chart and say, okay, we're 1-inch pipe. We're roughly at about almost 21 foot of head loss per 100 foot. Now, granted, I just rounded it up. We're looking at 15 gallons per minute, but in this case, we're just going to use the 20 as our number. So going forward, we're going to plug those in and see that in this case, 1.25 inches is going to be a friction loss of about 5.1. And then as our system pressure, we start adding all those up and plugging those numbers in. We eventually come up with a total of 297 foot of head loss. I round that up. And in this case, our TDH, I'm going to use 300 as our target point. So next, we're going to go look at an actual curve. Okay, and I'm going to try to get as close as I can to that desired gallon per minute we're required for that system. So when we look at this, the 15 will definitely hit what we need. Now I can get 15 out of this 10. It's pushing it, kind of towards the right side of the curve. I could definitely do the 20. It's going to be, kind of pushing back towards the left-hand side of the curve. So I've got basically 3 pumps that I can use here to achieve my goals. So if I do have the option for the 15, I'm going to grab it. And so I'm going to take a look at it, and I'm going to make sure that I'm somewhere in the best efficiency range. And that's ultimately where you want to try to strive to be. And as I pointed out, a 5 gallon per minute, not going to work. Its highest level it can ever pump is about 7.5 before you start damaging the pump. The 15 is ultimate where I need to be. The 25, I can still do pretty good, but it's going to be down here in the lower section of the efficiency curve. So I want to try to keep an eye on that, and the reason I bring this up is sometimes our suppliers just don't have the product on the shelf. We're in a pinch. We need to get this up and running. So it does, pique our attention to look at other alternatives. Now, as we start trying to build more pressure, you'll notice that the stage count gets larger. Okay, and as it gets larger, meaning that we're trying to push more pressure, so does the horsepower. Okay, so the horsepower will climb as the stage or the length of the pump grows. We are trying to achieve pushing a certain amount of volume to match a certain pressure or head requirement for that application. Now, once I start looking at sizing this system, I've picked the 15 gallon per minute. And as you can see, I've went up the left-hand side of the scale, which is our TDH. I've brought it across till I hit basically my 15 gallon per minute intersection. And I noticed that it's really close to the 1.5 horse. So if I was to go back a couple of slides where we were looking at the pipe size going over to the house, I believe we had 1 inch in there. So if we were to just upsize that, that would buy us a little forgiveness there and allow the TDH number to drop a little bit. I would probably get away with that 1.5 horse. Now granted, if we were to intersect that curve, we're only going to get about 14 gallons per minute, which could I live with that? I sure could. But if we absolutely needed 15 gallons per minute, what's going to happen is we're going to have to step it up. Okay, so if we go to 300, we come across and we intersect that 15, it's not quite a 1.5 horse, but if we step it up to 2 horsepower, we can clearly achieve that. Okay, it's going to hit, now granted, we're going to get about 17 gallons per minute on that particular TDH number. Okay, so I can use that if I absolutely needed to make sure I had 15 gallons per minute going to the home. Now, here comes the dilemma. Okay, the dilemma is sometimes we don't often look at the tank size. Okay, and since this pump is going to provide us 17 gallons per minute, what we're going to do is we're going to look at what tank is necessary to allow a 1 minute run time for the motor. All submersible motors need at least once they start, they need to run at least 1 minute. So if it runs 1 minute, I'm going to get 17 gallons of water. Okay, so the equivalent, if you're looking at the tank sizing, is on a 40-60 switch. To make sure that I've got enough to cover that 17, I'm going to need a 62-gallon tank just to allow me to run 1 minute. Okay, so that's how you figure up the tank size. And so this is where I run into a lot of cycling issues. We sometimes often undersize the tank, and therefore you're going to cycle the pump and motor more than what the manufacturer recommends. So you've got to be very careful there. Now, as the TDH goes up, so does the horsepower. And of course, I put a little bit of, some formulas in here. I hardly ever use that, but that's how it calculates the horsepower. It's looking at, what are we lifting here? Okay, so that does come into calculation, and there are formulas for it. So the way you work this formula is your TDH times your flow divided by the pump efficiency, in which I've got to tell you, the pancake style are very puny. As you can see, I've already reverse mathed this, and that particular pump is only 64% efficient. Okay, so not very good. It's not something we want to brag about. Hence the reason you don't see a pump efficiency curve up here. Usually they'll put one up here that shows, where that pump efficiency is. But in this calculation, we're figuring 300 or TDH times 17 divided by the efficiency, and then the 3960 is basically a conversion. So it says that this is equal to about 2 horsepower. Okay, now there are other things that we can take in consideration when we're looking at this horsepower range, and most of the time the pump manufacturers is pushing the envelope. They're really loading these pumps up, which translates into loading the horsepower up too as well. But that's a totally separate class that we would have to go through. But in this exercise, it says that we are right at 2 horsepower. So that's a formula that you can jot down. Now, the other thing is, I see a lot of times contractors will use these tables. Just be wary, because these tables do not take into consideration friction loss. Okay, I always like the curves better because I can see where everything is falling at on the curve. I can see how close everything is, and you can do the same thing here. If there's no numbers out there, that means don't be there. You can't be there. Typically, the grayed out area is where we want to keep your efficiency ranges. But just remember that these numbers here are from where the water level is pumping from, not where you're setting the actual pump and motor. Okay, so keep that in your mind. So if we were to break that out, just going back to that little cheater chart, lift is 158, or pressure is 60, and we're flowing 15 gallons per minute. So if we go back to that table, it's roughly saying the same thing. The only thing is, the difference is we're not looking at where the pump is set. Okay, so you got to be careful there how you look at these tables versus the curves. So in closing, we had discussed basic pump design, the bowl and the impeller, how to figure up gallons per minute, how to determine your TDH, and then we selected a pump. For those of you that want to do a little bit more investigation, I welcome you to visit our Franklin website, which is listed as franklinwater.com. Christina, I'd like to turn it back over to you for that 10-minute break. Did I stop sharing at this point?
You can, that's fine. Thank you, Dave. All right, everyone, we'll do it's about a 10, 11-minute break, and then we'll come back in and get going. So feel free to go stretch and get refreshments if you need to.
I'm sorry, Christina. I should have asked if there was questions that needed to be answered.
Not yet, Dave. I don't see anything.
Okay. All right. Very good.
Hey, Dave.
Yes, sir, Mark.
How you doing?
I'm doing great, sir.
Hey, quick question. Um, is there any difference at all between the FPS pumps and the JRD pumps?
Okay. JRG.
The JRD.
Just the old. Yeah, you have to tell me what that acronym is.
So you got the FPS. Maybe I don't
Yep.
know.
Yep. FPS is one of our brands. Yes.
The FPS, and then you got the J class.
Yeah. Yeah.
The JRD or JRS? I forget now.
Yes, sir. So to answer your question there, Mark, the difference in that is basically how engineering labels where the performance is. And if you were to overlay those curves, which you're going to laugh a little bit, but it's the same hydraulics.
Right.
They instead of reinventing the wheel, and I don't know what the whole marketing deal behind this was, but um, they are eventually the same hydraulic curves, and they were just trying to, hit I guess a performance point. And I don't see, honestly, between me and you, there is no difference in that, other than just the labeling of the pumps.
Gotcha.
Yeah, and again, I can't speak for engineering. They do some weird stuff, sir.
Yeah, we got to looking at that the other day, and I'm like, the pump curves are identical.
Yes, sir. They overlay really right there on the money. So,
Right.
as a manufacturer, I see how they are trying to differentiate the different pumps from one another. But then you also got to look at inventories. And so they look at, okay, we have this one particular hydraulic, um, system, and how can we introduce another product, but yet not have to carry the inventories? And so that's my ideal behind marketing and how they're going to, to show you this in the pump books. But ultimately, they're the same hydraulics.
You there?
Yeah, were you able to hear that, Mark? It's the same hydraulics, just we're private labeling the pump ends
Gotcha.
to give you to give you differential. Okay, so
Right.
one customer to another.
Okay. All right. Good deal. Thank you, Dave.
You're welcome, sir. So I started sharing the next presentation. Christina, can you see it?
Yeah, we'll see it momentarily. This is about to run out and it'll pop up.
Oh, okay. Sorry, I didn't know it was on the timer.
You're fine.
This time I think I chose the right one. Presenter mode.
Oh, good. All right, everyone, we're going to get ready to get started on the second session. And it's all you, Dave.
All right, thank you. So welcome back. This is part 2. Let me see here. I got to turn on one function here. All right. So welcome back. This is understanding stray voltages. This portion of the presentation will be dealing with using your meters and a little bit more advanced training on identifying safety issues. And as I go through here, I'm going to introduce basically one new meter that may possibly help identify some issues when dealing with problematic sites that are causing stray voltages, the potential for shock. And again, the whole purpose of this is your safety. What I typically try to recommend is as a bare minimum, to have one of the safety pins. And what this device does, and they're relatively inexpensive. Now, granted, you can spend a lot of money on these. I think I've seen a couple of these, brand names listed, somewhere around $20 to $30 a piece. But in most cases, the one that I'm showing here, I think it's like under $10. Which, if you look at your safety, $10 is not too bad to spend. And before you touch it, I always suggest test it. Test it before you touch it. There's some kits that you can buy. I honestly, all 3 of these I have in my toolbox. And what it's going to do is, before I actually turn a disconnect off, or I open up a metal cabinet, or if I touch a device, before I do that, or even the plumbing in most cases, especially if it's metal plumbing, I'm going to take my pin and I'm going to test to see if there's some kind of leakage going on there. I'd much rather for the pin to beep at me or flash at me is for me to touch it and get a tingle. And in some cases, that tingle could translate into something more severe. So you want to be very careful there. Now, there are some advanced tools out there. I don't typically name drop, but as you can see, it does show Klein on there. But they'll indicate, what the voltage is. And I recommend, that, if you're dealing with a pumping system and you're venturing out to the well house or the building in which, the controls are located, test some of the circuitry there. Just make sure, that it is functioning correctly. That might be the issue altogether. Someone might have come in behind the electrician or the building contractor and added something and not fully understood how it was supposedly needed to be hooked up. And I've run into this situation before. And what this meter particularly does is, green light means that everything is connected correctly. Red light means, hey, you got something, not correctly attached, and or you're borrowing something such as a safety ground to, and you're running current through it. So you want to be very careful. That's kind of what we're going to harp on here in this hour presentation. Now, when it comes to your meter selections, your common meters that you're going to have is a multimeter, and usually some kind of amp meter and or fork style device to check your amperage and or frequency, and then a way of checking the wire, okay, to make sure that you don't have any ground fault issues, because that in itself can contribute to leakage voltage or stray voltage issues. So this instrument is designed to look for those pinholes. If voltage is getting out, this meter is going to find it. Okay, and I'm going to walk you through that. Now, along with these meters, there's other functionalities that these things can do and or be used in tracking down chromatic, problem sites and issues. And I'm going to cover each one of those. So the first thing we're going to look at is basically our multimeter. Now, a multimeter, its term multimeter means that back in the day, you will have to have a meter for just about every one of these functions, checking AC voltage, checking DC voltage, checking and conducting an ohm test. So in early days, you had to have a meter for each one of these. And so a lot of meter manufacturers took that technology and made one meter to do multiple functions, hence the term multimeter. So in this case, one of the things that we can basically test for is a diode test. In most cases, your multimeters do have that functionality. It's kind of hard to see here on this picture, but I've taken the picture here and blew it up to show you the symbol. But what we're looking for here is a diode test. And a diode, if you can think about it compared to a water system, is basically an electrical check valve. It allows the flow of electric to go one direction, but then not back the other. Okay, so in our testing, especially when it gets to some of the advanced controls like drives, VFDs, we can check the components inside to see if there is an issue on the incoming side or the outgoing side or both. And that'll help us determine, what to identify and what our next procedure is going forward. But on top of looking at DC voltage, looking at AC voltage, we're going to now look at DC, a diode test, and determine what's going on in that system. But before we get started, I'd like to at least stress the issues that I see currently in today's market, and that's our power supply coming in. Okay, back in the early days, when electricity was spread out throughout the countryside, it was delivered with a tolerance of plus or minus 5%. That is the supply voltage. Okay, and nowadays, because we as consumers are using more electronics, we have more devices, gadgets, and everything else plugged up. There's also been some talk about adding, EV cars, electric voltage cars, and therefore, using a power supply to, charge those back up. We're going to put even a bigger strain on the electrical system that is now here. And what I like to point out is, the Department of Energy is basically the governing and regulatory body that most power companies have to answer to. And as a manufacturer, we get our information from them, especially if you're trying to build a piece of equipment to run on what's being provided. So in the early days, 120, 208, 240, 480, 600 volts, that was our nominal voltages. And the power companies were pretty consistent with keeping that right on target. Nowadays, what's happened is because as we as consumers, and then the fact that they have branched out pretty much everywhere nationwide, you don't have any areas too often that do not have a power pole or some kind of voltage supply there. And to make sure that there's voltage there on those longer runs and those places that are, what I refer to as out in the boonies, they crank the voltage up. And to give you an example, this 240 volt supply, about 25 years ago, I had, came out in the field service, and I noticed that, voltages were constantly around 245. Now, 20 years later, I noticed that they're hanging and hovering around 250. Okay, well, for those of you that don't know, most of our equipment, we try to nameplate about 5% under that. And if they start drifting too far, what happens is you can cause issues with the motors burning out, problems with the wire. You know, that just opens up Pandora's box for all kinds of issues. And so going forward, we as contractors, especially on the water well side of the business, have to pay more attention to this because the equipment is not changing. You know, as far as we're concerned, the Department of Energy still lists all these supply voltages, the power companies, and I can name a few. Yeah, I don't care to name a few. Duke Energy, Appalachian. You start getting some of the smaller co-ops. There's a number of them. Indiana Michigan Power. You know, there's TVA, Tennessee Valley Authority. There are a lot of major power suppliers out there. And so far, year to date, they have not reported to the Department of Energy, which is where we get our standards to build our equipment around. Okay. They have not reported that they are cranking this voltage up. So if you ever hear, you know, if you check the system out and they tell you, oh, we're allowed to be there. No, they're not. That tolerance is not changing. I welcome you to go to the Department of Energy's website, do your own searching. There are plenty of entities out there that can guide and help you. Like I said, I'm a firm believer in Google. I'll research and go through the necessary steps to, you know, to make sure that everything is in compliance. And if you ever need assistance, please don't hesitate to holler at me. I've got a folder an inch thick that's got all the do's and don'ts in it. But it's very crucial that these voltages stay in check. Therefore, the manufacturers can still continue to build their products without having issues. So with that said, there are several places that you can check that voltage. Sure, you can go right to the breaker panel itself, check the voltage there and make sure that, you know, it is where it needs to be. The voltage supply coming in most cases is plus or minus 5%. Now, we give a little bigger tolerance than that on our equipment. Well, we're allowed plus or minus 10%. So when you're at, say, a pressure switch, a control box, or even a panel, we're measuring that voltage coming in, it should be within that plus or minus 10% of what the equipment is rated for, not the power supply rating. So in example, if you're hooking up a 230 volt system, you want to stay somewhere between 207 and 253. That is the norm. If it ventures outside there, you start having component failure, you start stressing, say, the wires inside, some of the other protection devices start misbehaving. So you can have all kinds of issues start popping up if that is not in check. Wire side, or I should say the wire threshold. Most of the stuff that's rolling in here in the United States and is produced here in the United States has a 600 volt rating. You'll have to be wary because there is a lot of offshore wire that comes in. Make sure and pay attention that is still rated under the UL certification of 600 volts coming in. What you'll typically see is some of the foreign wire coming in because they're used to 50 hertz. They carry a threshold of 500 volts. So that would be getting you in trouble if you were to say hook that up to a 480 volt system, because in most cases those run in the 490s to almost 500 range now. And if they have any kind of spikes or transients rolling down the line, that could cause wire burnout. So you want to be very careful there. That extra tolerance is built in there for those issues, transients, and then, you know, any kind of switching action that may happen on the main lines that can cause spikes. The wire threshold is very crucial. So as we go through this presentation, I'll show you how to check for that and also some of the meters to use in those cases to make sure that wire hasn't been compromised. But the test that I referred to on the diode test works very well on drives. And as you can see here, I'm showing you a couple pictorials of some drives that are out there. And the way you conduct this test is you're actually setting your meter on diode. And during this test, what what you got to remember is this is basically a DC test. So it is polarity sensitive. And what I mean there is just kind of similar to a car battery. You have a plus and a minus. The plus is usually referred to as the red conductor, and then the minus, the negative, so to speak, is referred to as the black lead. Okay, so as that's connected properly on your meter, the way you conduct this test is it's opposite. Okay, when it comes to the polarity test, because it's an electrical check valve that we're actually testing, right? This is a diode test. We're checking to see if the drive has been compromised on the input side or the output side. So when we conduct these tests, what we're going to do is identify, in most cases, there's a DC bus connection. It's usually identified with a plus or a minus. Okay, so as you're connecting your probes, what you're going to do is with the red lead or the positive lead that's going back to your meter, you're going to put it on the negative post of the DC bus. And then with your black probe, okay, you're going to test the input of the drive, which is typically referred to as L1, L2, and L3, or in some cases, RST. Okay, so you'll check the input side, and then you'll also go over and check the output side. And the output side is usually referred to as T1, T2, and T3, or UVW. Okay, now in the Americas, we refer to our line side as L1, L2, L3, and our outgoing side is T1, T2, T3. The European standard is RST for input, and then UVW for the output. Okay, now granted, you may have a situation where it's a single phase in, right? So you'll just be dealing with L1, L2 and skip L3 because there's typically nothing hooked to that if you're using single phase coming in and you're using the drive to basically convert that energy to three phase. Now, the flip side of that is we're going to check the other direction too. So we're going to take the lead from our meter, the black lead, and put it on the positive DC bus. And then we're going to use our red lead and go to the same connection points. We're going to look at L1 through L3, and then also T1 to T3. I'm sorry I don't show you a picture up here of the other side, but it's just right here next to where you're checking the input side. The procedure is the same. What we're looking for is a value. Okay, usually it's going to be somewhere between 0.2 and about 0.5, 0.6, something very small. You're going to see a value. What you do not want to see is what we're showing you here on this meter. It says OL. That means over the limit. Okay, so right here I've got the no-go. So if you see 0 on your meter when you're doing this diode test on any of these functions, or you see OL, that means that diode is failed. Okay, and that will indicate whether we had a problem on the input side, the output side, or both. We could have had a problem on both sides. Okay, so that helps us try to identify where the potential issue may have come from. Now, if it's on both sides, in my personal opinion, chances are it came as the unit was running, it came in on the power side and went through the system and zapped both sides. Like some kind of electrical surge or spike or transient or even a lightning storm. As we get through this, the question always comes up, how do I identify what's been damaged on the output side? You know, the input side, pretty obvious, output side, not so obvious. So we make a meter for that. And so, oh, sorry. So as we go through the test, I also wanted to point out the smaller drives typically have that same ability to check for input on the diode test by going and identifying the DC bus connection. It's usually protected by a little cap. That cap will be identified as a plus and minus as well. And you're going to do the same functionality or same test. For the positive, you're going to put your black lead into that connection, and then you're going to go down and test L1, L2. You're going to check also your motor lead side, which will be, in this case, the red, yellow, black, which is going to your motor. So what you're looking for, again, is somewhere between 0.2 and about 0.5. If you see OL or you see 0, that means something is happening internally inside that controller. and it will identify, whether it's on the input side or the output side or both. Okay, so the smaller stuff can be identified as well. So the
Dave,
other meter, yes,
Dave, sorry. So to go back to when you were speaking about the power companies and them delivering higher voltages than what the motors are designed to take in.
yes,
Mark from Roar Drilling had a comment that he ran into a resting voltage at 9 a.m. of 249. Then at 8 p.m., the Pump Tech Plus was faulting out on over voltage. And essentially, the power company, had him bypass the Pump Tech until they could get it resolved. So the voltage and the supplies are affecting basically these pump systems to operate as they were designed.
that is
And for,
correct. So what happens in most cases when it comes to the power company, and I recently had been advised of this, it depends on how they're monitoring their lines. Um, I don't care to name drop Appalachian over here in Eastern Tennessee. I dealt with one of the engineers there, and to my surprise, they only monitor one of the three lines. And so what happened was, in this particular case, it was a protection product as well, and it was tripping, but it was on one of the lines that wasn't being monitored. So the way the power company regulates to make sure that their lines are not too high and not too low is they monitor the lines to see where they're at, and then they make corrections based on that. Well, if they're not monitoring the other two lines, they could be all over the place. They could be either high or low, and no one knows, only them. So what they did in this particular case was they went out to a substation and they just adjusted which one they were monitoring. I thought was kind of funny because now the other two are out of control. So on
Mhm.
down the line, somebody else's protection is going to be tripping that's pulling off those lines. So ultimately, we have a big issue with the power supply coming in. One is it's 1950, 1960 equipment that's out there. Now, granted, they've updated a few of them or brought some of them up to today's standards, but ultimately what we're dealing with is high voltage. I hardly ever see low voltage any longer. And they're doing this because we're putting such a strain as consumers on that power grid, and they have no alternative but to crank it up to make sure the person at the very end has proper voltage. And so I don't know what steps are going to be taken going forward. Whether the manufacturers are going to have to put more forgiveness in their products, which is going to ultimately change the design big time. That's something that we can address. And what's going to happen is more than likely they're just going to increase, basically take a horsepower of a higher rating and derate it, is what we're ending up going to do. And therefore you're buying more material. So that half horse that I'm showing you here in this little picture will now become basically it'll be a 3/4 horse motor that we're labeling a half horse, just to overcome this voltage issue here. But again, the Department of Energy, they are required to make sure that that voltage stays within plus or minus 5%. The Department of Energy has some rules and regulations on that, and if they ever get into that situation, I wouldn't hesitate to throw that up at them. But you've got to talk to the engineers, the line personnel. They've been totally instructed to say other things, and it could be their education too, what they're seeing. But the engineers that are responsible for it is the ones that you've got to talk to. And I've done a lot of communication with them over the years. Usually when you have a working relationship with them, they are usually more apt to, get in there and address some of the issues. Now, the word that I usually use quite often is infrequently. And what that means is they can be at those higher and lower tolerances for short periods of time every once in a while. Okay. They can't be there all the time. That's not a set standard. If that's a set standard, then they need to go back and report that to the Department of Energy, and some of the governing bodies that are out there. So that way, when we as a manufacturer build a piece of equipment, we know what the tolerance is going to be. But until they change that, we just have to deal with what we're dealing with. And And to Mark's point, I'd be very careful about unhooking the protection, because that protection is basically telling you, you've got a problem. You're going to burn something up if you're not careful. So you got to be very careful there. Does that pretty much answer?
Yeah, I believe so. Yes. And then there was a follow-up. So would it be appropriate and are you capable of adjusting the pump tech beyond the 253-volt threshold?
Okay. So some of the products have a fixed standard, and that is deemed by the manufacturer. Pump tech is our product. I don't typically try to, to harp on our stuff too much, but there are a lot of protection products out there, and in most part, the manufacturer knows that this is a fixed value, and so therefore there is no forgiveness. We know, and they know that if you go outside that realm, what's going to happen is you're just going to destroy the equipment. It's not rated for that. So some of the parameters are fixed. You just can't adjust them. And that product that was mentioned, that's fixed. There's no adjustment to it.
Okay. Thank you, Dave.
Yes. So switching gears and going to our next meter, I'm going to try to speed this up because I got about 30 minutes and 45 minutes worth of presentation. So the clamp-on amp meter, we've always used it to check amperage. Well, now that drives, VFDs, are becoming more part of everyday life, and because of the Department of Energy's requirements on efficiencies, we're going to start seeing more drives and phase conversion happening with even appliances inside our home. HVAC equipment is switched over. Just look at your washing machine. That is now a VFD. How do you think it speeds up, slows down? It's got a mini VFD in there. So amperage is directly related to how fast that motor is spinning. Is it at full speed? Because most of the amperages that are listed on the nameplate are at max speed, at its nominal speed. So going forward, if you've got a clamp-on amp meter, I would suggest that you have the ability to measure frequency, because frequency is directly related to what your amp draw is. So the slower this product is spinning, the lower the amp draw. And there is no manufacturer, even ourselves, have any kind of cheater sheets that show what that amperage is at a lower frequency. We just know that it's lower, right? So until it's at full speed or its rated speed, the only amperage that is published is typically its nominal speed amperages. So going forward, what I would suggest is that your meter have that functionality, and usually the clamp-ons are the best. To even go one step further, true RMS, root mean square, that's how it looks at the sine waves that are coming through the system. And so we want to make sure that we're measuring, basically the peaks without any kind of transients on there. So it's taken basically an average. But most important thing is, at 60 hertz, that's where our rating is going to be for the amp draw of that piece of equipment. One other thing that amp meter can do for you is trace down issues. So if we are having nuisance tripping at our controls, then we can try to backtrack and see if there is something else that is contributing to it. Let's just say we've got a breaker over here in the panel that keeps tripping. And so we look at it, and it may be pulling, I don't look at the 12 amps here, but let's just say it's a 20 amp breaker and it keeps tripping it. And then we know that our equipment over here may be pulling, the 12 or 13 amps that it was designed to run at, but then the 20 amp breaker is tripping. There may have been somebody that piggybacked off at a junction box and borrowing the power to maybe put a light on, or a receptacle, or maybe even a pump, a secondary pump pulling off that same supply, and hence the reason for the nuisance tripping. So we can start at where the power supply comes in, and then we can go to the next junction point, and then the next junction point, and then even down to the well itself to try to isolate where that leakage is. Because accumulated, if we have something tapped off at a junction box, after the breaker here, That, along with whatever's running downstream of it, will add up at the breaker. Okay, so we can just do a process elimination. Let's just keep on going down the line until we find out where that extra is coming from. Now, this is, according to, manufacturing, you want to make sure you stay within the recommended amp ratings of that piece of equipment. So in this case, a submersible, has typically 2 ratings. Most motor manufacturers will usually just stamp 1 rating on there. This is the max amps that equipment should pull. At some point, I'm sure we'll do the same thing. We'll get rid of this full load amperage and just say, look, this is the max amps. As long as you're under that, you're good to go. But we've not changed that yet today. And most manufacturers still list the same thing. They'll do the full load, which is the rating of that motor at its horsepower range. And then they do a max load, which is taking consideration a service factor, okay, which only affects the horsepower. So an example of a 1 horsepower, as we're looking at here, it has a service factor of 1.4. So that means that 1 horsepower motor is equivalent to 1.4 horsepower. Okay, so if you were running it into that 1.4 horsepower, you're going to pull 10.4 amps as its maximum. Okay, if you're running it lower and you're running around the 1 horsepower range of that motor, then you're going to pull 8.2 amps. Okay, so if you remember back in the calculations we were looking at in the earlier presentation where I was showing you the horsepower formula, where you took your flow times your TDH, you divide it by the efficiency, and then that 3960 constant gave you in that exercise a 2 horsepower. So on a 2 horsepower, I would expect, I'm not showing one here, but I would expect that the 2 horsepower range would be in its full load amperage range here. So when I clamp onto it, I would expect to see in this area here, that motor pulling that amperage. If it's not, then I want to start looking for some issues. Pay attention to the motor manufacturer's recommendations there. They will list, what that maximum is. Now, to start our troubleshooting, as we started looking down through this system, the overload protection was tripping. Well, as we started investigating it, as you can see in this picture here, we're checking the motor amp draw, which was correct, but then the overload protection up here was tripping because we had the dial set to the correct amperage for that motor. But then we realized here we have a chemical feed pump, and it happens really often where, we're borrowing one of the power supply, which makes sense because when the contactor closes, it starts both the primary pump and the chemical pump. Well, that's not the correct way of doing it. The other dilemma we end up here with is we've got leakage voltage. And the leakage voltage is coming because the neutral wire and the safety ground are going over here and connecting to the safety bus. So we're actually putting that AC voltage as it goes alternating back and forth on that chemical feed pump. It's actually affecting our safety ground. Okay, so if we were to separate that or have some kind of issue, we could get electrocuted. We could get shocked because the chemical feed pump, if it's running, it's dumping or, using that alternating voltage through the safety ground, which is bad news. There should have been a neutral brought over. Okay, and then the other factor is this power supply going to that chemical feed pump. On side of some of these contactors, there's a secondary circuit over here on the side. It's kind of hard to see it in this picture, but if I was to blow that up, you would see there's basically another circuit there that you could use as that contactor closes. It closes a set of points to run a chemical feed pump. If you're pulling off here, you're doing 2 things. You're adding amperage, in this case 10 amps, okay, to this one line. You're going to throw this device into either an unbalanced situation or an overload situation. And so it's going to trip. And at this point, when we took this off of there, system ran flawlessly. Okay, so the ideal here is to trace down to see where this dilemma, and it happens often. We also run into situations where the pump house Somebody goes in behind the contractor and say they want to put a light in there and or plug up a fan or some kind of heating element. Well, they end up tapping off the power supply and just pulling off one leg, and then they take the return, especially if it's a 115-volt load, and they take it back to the safety ground instead of a dedicated neutral. The neutral is designed to carry current, not the safety ground. Safety ground is there to um, uh, cause the overload protection to trip. And if we're using that, then we're energizing the system. So we can cause potential shock hazards at this point. So we want to be very careful there. The other meter that we're accustomed to using is our ohm meter and checking for resistance. We can also do using the insulation tester, which is referred to as the Megger. When we're checking these, basically all we're looking for is to make sure that something hasn't happened to the windings or the wire itself. And again, you can always refer back to the manual, the manufacturer's manual, and see what those values need to be as we're checking that circuit electrically. Wire sizing and breaker sizing, some manufacturers produce those, and you've got to pay very good attention to what they're suggesting there, because this is based off of National Electric Code values and tolerances. So always pay attention to the manufacturer's recommendations going forward. Going on if we're looking at a drive, going from the drive to the motor, typically there are filters inside the drive, and we want to be very careful there that we've not exceeded the threshold that those filters are designed to work at, and that's typically around 1,000 foot. Anything more than that, you'll have to add additional equipment, and that's usually in the form of a sine wave filter. Those will help suppress any kind of reflective wave or any kind of voltage spikes that may occur with a drive. The other function that you can use your resistance or your ohm meter for is checking a spool wire. Now they do make a meter for that, but no sense buying additional equipment because you've already got a meter that's capable of measuring that. And the rule of thumb is that what you're going to do is you're checking two conductors. Okay, so it has to be at least a 2-wire. If you're checking a single wire, there's other ways of doing that, but you have it to have at least 2 wires, okay, to test. One end you will wire nut together or connect together somehow, and at the other end you're going to go across it with your ohm meter. And the example that I've popped up here, let's say we're looking at a 10 gauge wire. And so I pull up my chart and I'm looking at a 10 gauge wire, and it says for every 100 foot, okay, as you can see here, every 100 foot, I'm going to get a resistance value of roughly about 0.214. So when on a spool wire, I go out here on the end where there's typically the first part of the wire sticking out. I'm going to strip it back and I'm going to put a wire nut on it. And at the other end, I'm going to put my meter onto it. And in this exercise, I got 1.3 ohms. Okay, so I know it's a 10 gauge wire. So 1.3 divided by the 0.214 says I roughly got 6. So 6 times 100 says I've got about 600 foot of wire on that spool. And so that's how you would determine how much is left on there. Because I've seen it before where contractors have cut so much wire off, put a sticky note on there or write on it. Now, granted, some wire manufacturers actually print on there, the distance of wire. But if you've taken it off, put it back on, and maybe it's gotten smudged or some other issue with it, you're unable to read it. This is a quick and easy way to determine how much is on there. But as I show you also in this picture, I'm getting 5.5 ohms. If I was to divide that out, it says 25 or equivalent to 2,570 foot. I know, no way that's on there. So that tells me right off the bat I've got something wrong with my wire. Okay, so it can also help you troubleshoot that there's a problem. And the misconcept is, okay, it's brand new. Well, yeah, manufacturers make mistakes. We're human. Things can happen. I was recently at a job site where the wire was blemished. They identified it, and apparently, whoever rolled it up didn't catch it, and it actually went out in the field. So things happen. So this is just one way of checking and proving out, what's going on with the system. Insulation test, I got to say, is the best way of determining any kind of breakdown in the wire. When you're doing a splice kit, honestly, I would probably have taken that motor and pump and put it in that barrel of water too and tested it all as one unit. But you can check to see when you do your splices. Sometimes we will do those in-house before we take it to the job site. One of the things that I always suggest is before you do a splice or a tape, tape that splice up or shrink tube it, is to clean it. Oftentimes we overlook the simplest things, and if we were to clean that lead, that assures that the adhesive is going to stick a lot better to that material and less likely to have any issues. Because in this point, this is a lot of time and trouble to pull this back out just to fix a splice. So one of the things that I try to do my due diligence is making sure I clean it before I attach it and or shrink it or tape it up. Make sure it's clean before you do those. But the insulation tester is a very wonderful tool, and it's designed to look for those type of issues and problems, pinholes, and how well we've put our splices together. Other things in the system that could cause our systems to misbehave and act up, pre-charging the tanks, that can cause cycling issues, whether it's a submersible or an above ground piece of equipment. A lot of times the end user does not realize that, we've lost a little air and we need to, add back that air to ensure that cycling doesn't occur and that system runs flawlessly. So just as an FYI, those are some things that can cause, the motor to twitch in the well, constantly start and stop, which can cause, the motor windings inside to short to the shell, hence the leakage voltage. We've got some kind of leakage going on because the system was allowed to cycle too much, damaging the wire, either the drop cable and or the windings inside the motor, and it's allowing that voltage to seep out through the shell and basically energize most of your metal parts or even earth, ground. That can also be carried through the ground. Animals are more sensitive to anything when that particular problem pops up, whether it's some kind of mechanical device and or electronic device. We've got to be very, very careful there that we identify those leakage voltage situations. I always recommend, keeping a hold of the manufacturer's guides and manuals. They have a lot of preventive maintenance suggestions in there. They have a lot of, tolerances and procedures that you must follow to get, dependable operation out of your systems and extend the life of your equipment. My most favorite subject is dealing with grounding. It seems like for the last 15 years, I've been dealing with grounding quite a bit over the years. I've had to do a lot of research, a lot of documentation, and things that I've had to help contractors and or electricians and other professionals identify issues and problems. But the one that I have the hardest time with is the way grounding is allowed to be done in today's markets. As you can see here, I've got it highlighted. A lot of times the grounding media is allowed to be the concrete or footers. And honestly, I've done the research. If you do the research, I think you'll find the same thing. But in Article 250.52A3, the NEC says that you can use the footer. Now, there spells out some requirements there and links and things like that and how you properly bond. But ultimately, you're using the footers in your foundation as that grounding media. Well, I've got something that contradicts that. It says, look, concrete is a poor conductor of electricity. Okay. It's more or less classified as an insulator. Okay. So I'm not sure how they get away with this or who wrote that part of the code, but you're going to start seeing more of that in today's markets. And I'd be weary about that because that is not, you're going to look for more, you're going to see more shock hazard. You're going to see more problems with equipment, especially if they're using, the footers as the media for grounding. And the reason I bring this up is we as water well professionals we have the best ground rod, and that's that motor and pump that is in that water strata. And if that's allowed to be the grounding media, what's going to happen is all of our controls are going to, at some point in time, be hit or damaged due to improper grounding at the service entrance. To go one step further, I don't believe the electrical contractors and the building contractors talk to each other, because we put gutters and overhangs on the house to keep moisture away from the foundation, as this article shows you right here. So it's kind of a, a two-sided thing here where both of them are negatives. And so I try to point this out when I run into these situations where, it's potential shock hazard, we're having leakage, we're having issues with our controls, pump and motor failures. This is the first thing that I look for. And this is the first thing that I point out to the homeowner and building contractors is, look, this, even though it's saying it's okay to do this, here's the Pandora's box that you just opened when you do this. And so, anyways, I just want to make sure that everyone's aware of this and understand, some of the problems you're going to run into out there may be contributed to things that may be out of your control. But we need to be smart enough to advise and show the homeowner, look, it's this is what's happening. This is why I'm here, is because these codes are being followed, and I don't believe that they've had any field exposure and or experience when they wrote this code, because it's pretty clearly obvious if you've been out in the field long enough to understand just the basic concepts here. So proper grounding, I always try to make sure that there's ground rods out there, try to make sure that clamps are actually clamping and not broken or missing. And again, what I try to point out here is that, our submersible pump casing, is in a water strata. That's the best ground rod you're ever going to have. We don't want that. We want to make sure that the ground rods are serving the purpose, that they're doing like they're supposed to. And if they're not, then we're going to see a lot more failures over the years. If we look at animal confinement, one of the websites that I'd encourage you to go to is Duke Energy's website, and look up tech tip number 9. They talk about animal confinement and, animals being shocked. If you've got poultry farms, dairy farms, hog farms, those type of environments where, the animals are drinking water, if there are stray voltages, what's going to happen is once they get tangled, they're not going to drink. If they don't drink, they don't produce, they don't eat as much, they don't grow as much. So there's a whole list of things that can happen that leakage voltage can cause problems with. But I'd encourage you, to look at Duke Energy's tech tip number 9. They talk a little bit about the stray voltages. This is the meter that I was talking about that I added to my toolbox. It's a ground rod meter, and it's come in quite handy. It saves the shortcuts. And what I mean by shortcuts is there's another way that you can do the test, and that's at any control. You can disconnect the safety grounds with the power off, and you can check and see if there's one stray voltages coming in on that safety ground. If you see more than 1 volt AC, you should address it. Okay. I would not proceed to this second test, which is actually using your own meter. You're going to check and see what the resistance is from the ground well, from your ground rods to the water well itself. And what I want to see is low numbers, a couple hundred, couple thousand ohms. Now, people will ask, well, is this documented anywhere? No, it's not. This is through practical field exposure that I've conducted over the years. But I want to see low resistance reading. What that tells me is that the well ground, which is going out to the motor and pump, is just as the service entrance is just as good as that well ground. Okay, so the lower the reading, okay, the happier I am. You get up here around 886,000 ohms, something's wrong with the ground rods. More like it's probably a foot of ground or something of that nature. So you want to identify that and try to get that resistance down as low as you can. That's one of the things that I run into with the NEC. They're talking about putting a ground rod in. If it doesn't measure under a certain value, you're going to add a second one, but then they don't give you any numbers to reference it. The way that should work is because otherwise they're wasting my money. They're wasting the consumer's money. if by putting a second ground rod in, if you don't see any improvements, you just wasted your money because the second one's not doing any better than the first one. So if you don't see any improvements, keep going until you do see an improvement. That's kind of the point that I'm trying to make here. Things to look for out in the field, improper, grounding, okay, using a hose clamp, not even securing the grounding media, using the wrong materials. This particular picture here was actually inside of a pump house where I can assure you it's not moist in there. As you can see, everything's dry here. So you want to make sure that you're using the right materials, you're connecting correctly, you're bonding your equipment as it's showing here in this section here, Article 250-50 about bonding and making sure everything is tied back to one general location. Very crucial. And if this is not done, you open up the potential for leakage voltage and some potential issues with failing equipment. This was actually at a job site. They had multiple failures. Come to find out their surge protection was not working because apparently on this golf course, the mowers actually severed the ground wire that was connected to the ground clamp. Now this picture, just to keep everybody lively, is NEC says that you need to put a ground rod into moist soil, and this contractor thought, I'll just get a bucket of wet soil and stick the ground rod in. So that's my little joke for the day. Kind of keep you awake since we're almost in the final run here, but it's all about interpretation, all about checking and making sure things are where they need to be. Now, granted, as a water well professional, you wouldn't necessarily look for this issue here. That has nothing to do with my water well system. But in reality, inside this panel, there was surge protection that's supposed to be protecting your equipment, but it's doing a poor job of it because something had happened here. Okay. And yes, it may be outside your realm, but we need to be educated enough to identify this type of thing so we can bring it to their attention. Well, this is why the equipment failed, because the protection couldn't do its job. Okay. Because it wasn't even attached. So things like this can pop up. We also have to worry about situations where, potential shock hazards, the safety ground, what the power company refers to as NEV, neutral to earth voltages. Okay, so that's stray voltages kind of back there on that same picture that I showed with the animal confinement. Something's happening where that voltage is being leaked. Okay, now the power company does have the ability, even yourself, if you wanted to front the cost, but they've called it a neutral isolator. If you can't get the safety ground cleared up, the power company, as you can see in this picture, can install what's called a neutral isolator, and I assure you, those do work. I've seen them in practice. They do work. They will eliminate, any kind of stray voltages coming in. And I'll guarantee it, if it's some kind of animal confinement like dairy farms and or poultry farms, they're going to see a big difference. Okay, a huge difference. Now the ones that I plucked off of here, there's two different models. One's rated for getting ready of about 11 volts off of the safety ground, and another one, it's a little bigger unit, will get rid of about 22 volts. If it's any higher than that, typically there's something else going on in the system, and you definitely want to make sure the power company's involved there, getting out there and resolving any issues they may have. Now, with all that said, nothing we can do about this. Okay, if Mother Nature it's determined to surge something, you can throw all the protection at it you want, but you're not going to successfully get rid of it. Things like this happens: dog fence, knock trees down, power line issues, even burn up equipment at this point. So sometimes things are just out of our control, but the important thing to remember is, let's try to do as many as we can, check as many things off our list to make sure they are correctly installed and protected, and we'll get through it. Surge protection, I'm a firm believer in it, but ultimately you got to make sure you have good grounding. And we are not saying the well ground. We want service entrance ground to be the best grounding in the whole system. So with that said, I always encourage you to jot down two numbers. We have a world-class hotline team. 1-800-348-2420 can answer any kind of questions you have with the products that are out there and assist in trying to help, figure things out. And then keep my number around. I'm Dave Bumbleow. Number is 765-499-1165. And with that, I turn it back to Christina, and thank you very much. Any questions?
Thank you, Dave. Anyone has any questions, feel free to unmute yourself. We'll stay on for a few minutes. And I appreciate, Dave, for your presentation this morning. It was lots of great information, a lot of resources, and I'm sure a lot of contractors will get some good information out of it. So I appreciate it.
Thank you.
All right, well, I'll go ahead and, I do see someone on mute. Jay, did you want to ask a question?
I want to say, hey, Dave, just really enjoyed the class. Great content, really good information. Really appreciate you putting this on.
Well, thank you, sir, for participating. I know 2 hours out of your day, it's got to be busy for you all. And I do appreciate your time.
Yeah, it was well worth it.
Thank you, sir.
All right, well, thank you all. This will conclude today's course for Pump Basics and Advanced Stray Voltage. Appreciate Dave Bumbleow with Franklin Electric presenting today's class. I look forward to seeing everyone next Thursday for the DOT regulations for the water well industry. And this concludes today's course. Thank you.